Good evening everyone. Can you hear me? Is it audible? Hello. Can you hear me? Today we are going to discuss the maximum power transfer theorem. Let us consider the AC circuits. Vs and a source impedance Zs and the load impedance Zl, and Zs is equal to Rs plus J XS, and your Zl is equal to RL plus J XL. We need to find the conditions of load for a given Zs, that is the source impedance. What will be the maximum power transfer to the load? In an electrical networks, we are connecting various loads and the source has an inherent impedance. So we need, if you want to achieve maximum power transfer from source to load, then what should be the value of load? That is the criteria. Okay, so you can easily write the current I is equal to Vs upon Zs plus Zl, which is equal to Vs upon Rs plus RL plus J XS plus XL. Now come to total power delivered at the load. You know that from the power theorems, I am assuming that these Vs and I are in RMS or effective value. So power, you know that power delivered or absorbed by the load ZL is equal to magnitude of I square into real part of the impedance. So the power will be the magnitude of Vs square upon Rs plus RL square plus Xs plus XL square, right? So you know from the maxima and minima theorems, we want to maximize this power. We need to maximize the P. What do you know about this maximization? That dP upon dRL should be equal to 0 because the power is the function of two variable, and dP upon dXL equal to 0. We need to maximize from maximize the power, and we need to find the what should be the value of RL and should be the XL. If you do little math and apply, then you will find at last R of L, or let us do, okay, let us do, because we have P. What is the value of P was there previous page? P is equal to V square Rs plus RL square plus V square RL, right? We have left RL. So P was magnitude of V square RL plus Rs square plus XL plus XL square. This is, now take dP with respect to dRL. You know from the basic of differentiations. So these terms will be RL plus Rs square plus XL plus XL square into Vs magnitude square minus this Vs square RL into, this is the, there is no RL, so this will be the 2 RL plus Rs, okay, 2 RL plus Rs upon this total. Let's say I designate as the M, that is your M square, and when you equate to 0, you will have these terms, that is V square cancel, so you have RC plus RL square plus XL plus X of S square minus 2 RL, right, 2 RL into Rs plus RL equal to 0, right. So we need to find the RL. So RL, okay, take common RL from this, here you see here RL square plus RS square plus 2 RL and RS. Let these terms remain same. Okay, minus 2 RL RS plus minus again minus 2 RL square equal to 0. Then these terms and these terms cancel, and here 1 RL square, here minus 2 RL square, it goes to right side. So RL square is equal to RS square plus XL plus XS square. So conditions for RL is the RS square cos XL cos XS root over. This is the conditions for the RL. In a similar fashion, you can calculate, that is from dP upon dXL equal to 0, you can calculate your x of L is equal to minus x of S, right? X of L equal to x of S, and when you combine it, because previously we found RL is equal to RS square plus XL plus XS square root over. These two conditions, when you combine, you put these values here, so you find that RL is equal to RS. So you can see that for maximum power transfer, your Z of L is equal to RS minus X of S, which is simply ZS complex conjugate. If you have freedom to vary both X of L, that is the load reactance, and load resistance, you can vary and made equal to the, that is complex conjugate of the source impedance, if you have a freedom to vary both the variable. This is important for the quiz or short question, 1 mark type questions. But special case, when you have only one thing you are allowed to vary, when only one, you have ZL, the case 1, special case, when you have freedom to vary both XL and RL, then this is the case for the maximum power transfer. For example, for the special case, when you can only vary this, not this. Okay, then for maximum power transfer, we have already calculated RL equal to RS square plus XL plus XS square root over. Case 2, when only you are allowed to vary reactance of the load. Then for maximum power transfer, XL should be, as the case, minus XS, right? But what happens, only the load is there without any reactance. You have freedom to vary like this, only load, that is your R of L, right? What should be the case of, what should be the value of RL for maximum power transfer? You can easily see from the general relations. There is no excess, no XL. So that means here XL equal to 0. You can see that RL should be RS plus X of S square root over. What does it mean? Magnitude of source for the maximum power transfer. So let us consider what is the power, maximum power delivered. Okay, what is the maximum power transfer, or you can say the what is the percentage of power transfer at the condition of, or when the load is equal to complex conjugate of force impedance, or you can say that is, we can say the efficiency. What should be the efficiency for the case? We see that when ZL is equal to complex conjugate of ZS, so I simply becomes Vs upon 2 RL, because RS equal to RL, sorry 2 RS na, yeah 2 RS, and P max is equal to magnitude of I square into RL. In this case RL is equal to also RS, so Vs square magnitude square upon 4 RL square into RL, because RS equal to RL, so I directly written it. So Vs square upon 4 into R, Vs square upon 4 upon RL. This is the maximum power delivered to the load. So you can easily, this is the power delivered to load, and the power, that is power delivered by the source, it is the delivered to source, so delivered to load is this, and the power delivered by the power absorbed by the source is the same. So efficiency will be the, this is the delivered, that is the PL upon P in. So PL is equal to V square, Vs square upon 4 into RL, Vs square upon 4 into RL, and same amount of power is also absorbed by the source resistance. So this will be the twice upon Vs square upon 4 RL into 100. So you will see that it is 50%. That is, at maximum power transfer efficiency is 50%. What does it mean? That is 50% of the power is wasted in the source, its source impedance itself. Okay, so this is the for the maximum condition for the maximum power transfer, and every year, every alternate year, our frequency of the questions appearing in the GATE exam is very high from this theorem. What about for DC case? This is the AC case was there previously. What should be the conditions for the RL for the maximum power transfer? Suppose you have a network, okay, and here your RL, because DC case only RL low resistance, and you are connected. What should be the conditions for the networks so that we can get the maximum power transfer delivered to the RL? It is simply find the Thevenin resistance of the network. Find resistance of the network. You know how to find the Thevenin resistance of the network. So the conditions for the maximum transfer is the RL should be the R. Sorry. Good. Now case is the, suppose you have two networks. Or you can say two circuit, and the connection is like this. Okay. What is the, in this case, what should be the value of R, okay, for maximum power transfer? Hello. So what should be the value of R for the maximum power transfer for this case? That is circuit 1 or network 1 and network 2, and you are transferring power from network 1 to network 2. For example, it is a generating station. This is your transmission line. This is the distribution center. Power distribution network. Very basic concept of the power, electrical power system: generating station, transmission line, and distribution network. That is from where you get the power from the supply. So in this case, it is simply find the power delivered to this network 2. Okay. For that, you need to find the V, you need to find the I, right? So you will find the P equal to Vi, then you differentiate with the dP upon, differentiate with respect to R and do it equal to 0, then solve for value of R. Okay, it may not be 0. Okay, if it is 0, it is 0, but not always 0. Now move to the Telgun theorem. Telgun theorem tells about the total power absorbed equal to P to P delivered. Okay, that is, or you can say total power in a circuit is equal to 0. Whether it is absorbed or delivered, it will be 0. You can it is just a conceptual things. So we learn the superposition theorem, we learn the Thevenin's theorem, we learn the uh, Norton's theorem, we learn the we learn today, that is your maximum power transfer theorem. So with all these theorems, all other theorems are just, and also we have learned that is your reciprocity theorem in the last class. So we will discuss the some of the questions appeared in the recent GATE exam from the topics of network theorem. And for the network theory, it is enough to do all sort of questions, and you see how I am doing the questions which appeared in the previous year GATE paper. In the circuit shown below, the Thevenin voltage VTH is, okay, we need to find the Thevenin voltage. As this side is open, so this current is 0. So you can find with the application of any of the concept you learned, but I will use here superposition theorem. When only 2-volt source acting, only 2-volt source is acting. So the situation becomes ideal current source open, two, two, 2 and 1. So this is the voltage drop across the 2 ohm resistor is your VTH. So let's say it is V1, this voltage V1. So V1 is the voltage drop across the 2 ohm resistors. So potential division 2 upon 2 plus 2 plus 1 into 2, that is 4 upon 5, which is 0.8 volt. Now only 1 ampere current source is acting. Acting 1 ampere current source is acting. Will be short, voltage source will be short, will be open. What is the current flowing through this? Or you can say this one I1 and this is your V2. So I1 will be current division, because there are two path for this 1 ampere current. One is 1 ohm and this is the 2 plus 2 4 ohm. So current division relations tell that this current will be 1 upon 2 plus 2 plus 1, that is 5 into 1 ampere, which is 1 upon 5. So your V2 will be 2 into I1, which is 2 upon 5, that is 0.4 volt, right? 0.4 volt. Now when 2 ampere current source is acting alone, the situation will be like this. Two ampere current source, let's say this is V3 and this is your I2. So you can see again current division, one path here, one path here. So I of Q is equal to, this current is a 2 plus 3, 3, I2 equal to 3 upon 5 into 2 ampere, that is 6 upon 5, right? 6 upon 5 ampere, and your V3 will be the 2 ampere source acting alone. So V3 will be the 2 into I2, that is 12 upon 5, okay, 2.4 volt. So all the voltage is in the same orientation. So your VTH will be the, when all the three sources are acting, that will be the V1 plus V2 plus V3, that is 0.8 plus 0.4 plus 2.4, okay, 2.4. So that will give you the 3.8, 3.6 volt. This is the correct answer. Yes sir, yes sir, you are right. Okay, so it is clearly seen that you should apply the superposition theorem to get the result easily, that is to find the Thevenin voltage. This is a really a 1 mark question, right? So don't worry, the power has gone, but you may not see me, but you will definitely will study it, not an issue. Let us move to the next question. This is the GATE 22 question. In a linear two-port network is shown in the figure A. An ideal DC voltage source of 10 volt is connected across the port 1. A variable resistance R is connected across the port 2. As R is varied, the measured voltage, measured voltage and current in at port 2 is shown in the figure B, this one. It tells that this measured voltage V2 and I2 has the relation like this when R is varied. That is the plot of V2 minus I2. Why minus I2? It's showing that this is the voltage and the current in this direction. This will be minus I2 convention. If it is plus I2, this one, so this direction will be minus I2. That is V2 minus I2 they have been given. Obviously, they have given the value also for 2 point. When the variable resistance R, again it is telling, if the variable resistance R at the port 2 is replaced by the load shown in the figure C, the current I2 is milliampere, in milliampere. That means when you replace this R with a variable resistance like this in the figure C, you just connect here. They have been given all these conditions, and now you are going to connect this to these networks. So it asks you what will be the value of current I2. After studying this question, you should have got the idea how to proceed. You can easily see that because it is given a network, right, and the voltage and current relation has been given. When the voltage, when current is 0, voltage is 5 volt. That means a open circuit condition is given. Open circuit condition is given at the port 2, this side, at the point AB. Similarly, it is a slope. The slope will ultimately meet at the line when V2 equal to 0. That means a short circuit point has to be find out. And open circuit voltage, you know, the network, if you find the open circuit voltage, it is the Thevenin voltage at the point A and B, and the short circuit current is the Norton current at the point A and B. And you know rest of the things. You can represent whole of this network into a Thevenin equivalent circuit. So let us do it. So VTH, that is VOC, VTH is equal to VOC. What do you mean by VOC? Open circuit voltage at A and B at the point port A and B, point A and B. You can clearly see that when I2 is 0, your V2 equal to 5 volt, that is VOC is the 5 volt. Everything is given in the question itself. So, equation for this, V2 minus 5 is equal to slope, that is minus 1 upon 4 milliampere into minus I2. This is the equation for this line. So V2 is equal to 5 minus 1 upon 4 milliampere minus I2. Minus I2 I am taking as a variable, that is it is flowing into the resistor R. Now how to find the short? Let your V2 equal to 0. The short circuit current, which is minus I2, is equal to, what will the short circuit current? 5 up into 4. You can see when V2 is 0, 5 into 4 milliampere. That is short circuit current is your 20 milliampere, minus I2 because this current is flowing against the indicated direction. The indicated direction, as I have told in the beginning. Okay. If you one thing you remember, you have the VTH, and you can, I have told you how to find the Thevenin resistance, open circuit voltage upon ISC. Okay, that means a network has been given, your the same point A and B, this is your open circuit voltage, and we have now found the short circuit current. So open circuit voltage is 5 volt and short circuit current is the 20 milliampere, that is 1 upon 4 kilo ohm, that is 0.25 kilo ohm, right. Now if you have found the Thevenin equivalent, then connect this source. You have found the Thevenin equivalent of the network as 5 volt, that is 0.25 ohm, sorry, kilo ohm, kilo ohm. This is your point A and B. Connect the network given in the figure C. What is the values there? Value is 1 kilo and 10 volt. This is your 1 kilo and this is 10 volt. And what is the direction of I? Direction of I2 is this. So you can see that easily I2 will be the 10 minus 5 upon 1.25. So 5 upon 1.25, that is 4 milli. The answer is 4. Okay. So conceptual application. So you can hope you can easily do it. If you could do, if you understood, then practice. Hopefully you all have understood this. Okay. Let us move to the next. Then volt is nothing there, no use. In the circuit, the maximum power in watt that can be transferred to the load RL. Okay, this is the load RL and you need to find the maximum power that can be transferred into R. So you know what should be the RL. Okay, first you need to find the Thevenin, you need to Thevenize, let's say this is A and B, you need to Thevenize it. So let us find the Thevenin voltage. Got here, find the Thevenin voltage, that is simply voltage across J2 ohm impedance. J2 upon 2 plus J2 into 4, right? All the value has been given. See, the voltage is in the RMS. So 4J upon 1 plus J. What is your RTH? RTH is equal to parallel of 2 ohm and J 2 ohm. 4J upon 2 plus J2. That is your 2J upon 1 plus J. Just now we have studied for maximum power transfer when the load is purely resistive. So RL is magnitude of RTH or source impedance, which is 2 upon root 2. Is the take the magnitude of RTH 2 upon root 2, which is root 2. Right? Let us proceed again. So now my circuit becomes the RL, ZTH, VTH. Now I will find the I. I is equal to VTH upon ZTH upon RL. For maximum power transfer, your RL is root 2. So what is the VTH? VTH we have just calculated, that is 4J upon 1 plus. Clear? Then ZTH 2J upon 1 plus J plus root 2. Right? Now your I becomes 4J upon, when you do this, that is the numerator denominator, that is the denominator 1 plus J cancel, 2J plus root 2J plus root 2, that is 4J upon 2 plus root 2 into J plus root 2. Right? So power, because they ask the what is the maximum power transfer, that is all the RMS value, I magnitude square into RL. I magnitude square is the 16 here upon 2 plus root 2 square plus 2 plus root 2 square 2 into root 2. This is a simple calculation. Use your calculator. Okay. So you will get 1.65. Here, very simple. We first found the, because we know that we need to find the source impedance. For that we need to find the Thevenin impedance. We got the source impedance. Then we found the we need to find the voltage source voltage, so VTH. Then we know that it is a only resistive load here, only resistive load here. For only resistive load, for maximum power transfer, the condition we have just learned, that is your RL is equal to magnitude of ZS, that is RTS, which is root 2. Then find the current and magnitude into current in I2, and keep a look at the what they have been given. They are already given the RMS and you need to divide by the 2. Understand that. You should have a clarity in your mind and open your eyes and brain also, mind also. Otherwise you will come with the dividing by 2, even though you have calculated correctly, but you will be losing the 2 marks. So keep open your eyes and mind and work out. Hopefully you got it. Then we will move to the next question. This is a GATE 2017 question. This is a really good question. Consider the circuit shown in the figure. The Thevenin equivalent resistance in ohm across the P and Q. You have learned many ways to find the Thevenin resistance. That is, first one is the, because you have a dependent source, you need to find the V2 and produce the I2, divide V2 by I2, you will get the Thevenin impedance. Other way is the drive the 1 milliampere current, 1 ampere current, and again find the voltage. That voltage will be the numerically equal to the Thevenin. Another way you have studied, find the open circuit voltage and short circuit current. Just before we did apply that concept and divide the open circuit voltage by the short circuit current to get the Thevenin resistance. The way, or you can say which relation you need to put here so that you have a answer easily. So if I look at the circuit, it looks little complicated, and if I go by the finding the open circuit voltage or short circuit current, it may be little longer. Okay, and that is a zeroing, or you can reduce the whole independent source to 0 and find the I2. If I see that there is a parallel path and there are 3 current path, so it may be possible, okay, to do it easily, but I always follow the path of driving by 1 ampere current source. That is, I'll drive it by a 1 ampere current source and reduce this to the 0, because a independent voltage source, it will be shorted. That means this resistance has no effect on the circuit, you can remove it, right? Now you see that this resistor is simply across the voltage source, dependent voltage source of 3I. So you can easily write this current is 3 volt V upon I, that is 3I upon 1, that is the 3I0. This current is I0 and 1 ampere is coming. So this current will be the 1 minus 4I0. Okay, this 4I0 and 3I0 will be merged here. So this current will be the 1 minus I0. Okay, now we are ready to find out the, and this is the voltage V. If we find this voltage V, that will be the numerically equal to the Thevenin resistance. So I will apply KVL around this outer loop. Remember here, this is the sorted, this voltage source, independent voltage source, you should remember. So your V is equal to 1 into 1 minus I0, okay, plus 3I0, this way, 3I0, which is 1 minus 1 plus 2I0, which is equation 1. Now I will apply the KVL around this loop. Remember, this is not acting. Same way, 1 minus I0 into 1, okay, then plus 3I0 into 1 minus I0 into 1 equals 0. So 1 plus I0 is equal to 0 which gives you I0 is equal to minus 1, equation 2. Use the equation 2 in equation 1. So, V is equal to 1 minus 2, because I0 equal to minus 1, that is minus 1 ohm. That means it is acting as a negative resistance circuit. That means your ZTH is equal to, is it clear? See the powerfulness of this third method, that is the driving the circuit with a 1 ampere current source and find the voltage. So, with this we completed the Thevenin's theorem to learn. Then once you have learned the things, then only you can apply or you can think of multi-dimensionally. Understand? Multi-dimensionally. This question, if you find in any solution book, it will be a one page to the 1.5 page. There you will not learn anything. Anything you can learn. You cannot be even mug up this question. This question won't come again in the GATE exam. So what to do is do your innovative way or different way of doing the questions. Which one would give you the result very quickly, so that you can get the 2 marks and move to the next questions. And don't assume anything. First of all, many people have done they will find the right result. Ultimately they will enter 1 ohm. अरे ये रेजिस्टेंस कैसे नेगेटिव हो सकता है? अपना लॉजिक लगाएंगे, कभी नहीं लगाना, ठीक है? ये रेजिस्टेंस के नेगेटिव रेजिस्टेंस भी होता है, तुमको पता है कि नहीं मेरे को पता नहीं, बट देयर इज ए नेगेटिव रेजिस्टेंस डिवाइस. They have also useful circuit in the application of oscillators. Negative resistance, we intentionally do the negative resistance so that we can cancel the positive resistance, so that power loss would be 0 in that circuit or minimized. Yeah, there are you will whenever you will do the analog VLSI design, you will learn when implementing the solid state oscillators, you will learn how to design a negative resistance circuit, so that it can be connected to the oscillator, so that power, because oscillator, what is the purpose of oscillators? We will be generating a signal or carrier. If generating the carrier itself is consuming power, your critical device is the battery. Battery will be certainly drained out. You will be weeping. Whenever you see that in a red line of your battery in the mobile phone, then you are started panicking these days. Okay, to minimize that battery consumption or power consumption in a portable device, we design the negative resistance circuit, so that we can connect it in that oscillator in such a way it can cancel the positive resistance and minimize the loss in the circuit. This is also an interview question. What is the use of negative resistance circuit? So please read the books, learn the things. Okay. Doing excellency in your field requires lot of dedication and hard work. This is not a cakewalk easily, but if you put your sincere efforts, learn every day, and killer instinct to learn and apply the things in the problem solving, and you will be a great engineer in future. And refer the books also. With this we complete the class of today's class. Also we completed the network theorem class. In the next class we will discuss or we will cover up the resonance, another important topics for the competitive exam. Syllabus. Okay, if you want to excel in any field, we need to learn something extra. Even though they have not given, you may not revise for that, but dot convention is very well there in the electrical, obviously it will be there, and in the instrumentation also, but it is not in the electronics, but we will cover it up. Then we will move to the next topic, that is the transient analysis. Most frequently asked questions comes from the transient analysis. Okay, and that application part is in the all over the electronics, electrical instrumentation field. Transient behavior and steady state behavior of the circuit. If you don't know transient behavior, how will you calculate the rise time of a digital circuit? How will you calculate the fall time? How will you calculate the propagation delay of a gate? All these are the applications. Okay guys, keep learning, keep exploring the world of electronics with me each and every day. Thank you for watching my video. Please keep subscribing the channel so that more people can join and learn the new world of electronics. With this, we end the class. Good night.